Hello, hello. Greetings. How you guys doing? Hello, Michael. Welcome to the last week of classes. Very exciting. Good morning, Dan. Do most of your guys' classes have finals? Like, what kind of classes don't have a final? MAU 177, is that like SolidWorks or CAD or whatever program you guys use for CAD? When do you get to, what are you designing? What are you creating? Do you get to choose, or does everybody have to choose their own? Oh, awesome, that's great. I mean, Dan, what's your definition of chill? I mean, we learned a lot. Like, the content can be challenging. I'm glad you thought of it as chill, though. That's awesome. Michael, we've got one more class on Wednesday. Too much. You know, sometimes having the choice is 207 and 205. Is that that's not circuits, it's 202. Is that like advanced circuits with transistors and fun stuff like that? Signals and systems. Oh, I knew that. Signals and systems. Really? That doesn't have a final? I wonder if that's instructor preference in terms of this, the way things are in the virtual world. Yes, too much free choice, Squiddy. Sometimes it's nice to have some choices, but not an infinite number of choices. Like, do you want to eat carrots or broccoli? For most people, one of those would be better than the other. But you still get a choice, but it's not infinite. I learned that in parenting classes. Giving your kids choices, but not an infinite number of choices. Anyway, random aside. Well, it's the last week of classes. We have review all week. Today, I will be going through... I will be taking a system, and I will be solving it in all the different ways that we learned. There will be practice problems, or there's going to be a practice exam. It's definitely much more a practice exam than just practice problems like I gave you guys for the midterm. That will be released right after class. It's either at noon or noon 30. I don't know. It's going to be available on UB Learns. There's going to be a new folder that shows up under week by week material called Final Exam Material or something like that. And it's going to contain practice problems. It'll contain the lectures for this week, the links if you don't watch live. And yeah, so the problems will be released later. I will go over those problems on Wednesday, and then the solutions will be posted on Thursday morning or something like that. So this week, we just have lots to review. Hopefully you find it useful. Finals week next week. And then you'll be done. I bet turning in the programming project specifically for this class was probably a big relief. Homework 13, problem 1, part E. So part 1, or problem 1, I knew this without looking at it. Part E is talking about span. So if you remember, the span formula is the span of a set of vectors is a blank D space in R blank. So you need those two numbers. The first number comes from however many of those vectors in that group are linearly independent. So when you're talking about V1 and V2, that's your set of vectors, V1 and V2. That's your set. S equals V1, V2. So between those two, you need to figure out if they are linearly dependent or independent. So if one of them is a multiple of the other, or if not. Once you figure out how many are linearly independent, then you can fill in your second space. So it's a blank D space in R blank, which the R blank is just literally count however many numbers there are in V1 and V2. And you'll note there's 4. Same thing for B. Your set of vectors is now V1, V2, and V3. Figure out how many of those are linearly independent. And now that I think about it, you should be able to get that from part A, or A, B, C, and D. Given the fact that part A, B, C, and D tells you more or less which vectors or how many of those vectors are linearly independent or dependent. This stuff is annoyingly theoretical. It really is. It's useful. It shows up in the background in a lot of material. But a lot of it's just kind of like taken for granted. It's not explicitly used. So this stuff it's a little bit harder to grasp. But for part E, you're looking for the span. Span is a blank D space in R blank. The first blank comes from however many vectors are linearly independent. And then the second blank comes from however many numbers there are in each vector. I don't know if that answered your question any more than I did on Discord. Okay, let's go ahead and begin. So like I said, today is review. Since your practice problems aren't posted yet, and I want to give you time to do them, so I encourage you to at least look at them, glance through them, try them before Wednesday, if you have time. I encourage you to finish the homework, do that as soon as possible, and then go into the practice problems. But today, since we don't have the practice problems yet, I am going to go through one system of equations, and I'm going to solve it using as many methods as we have, or as we learned about. So just a little bit of a review. This is all the material we learned about. So for the final exam, we are just looking at linear algebra. So the first week, we went over vector algebra. So you should know how to find the dot product, not the dot produce, between two vectors, the norm of a vector, the unit vector, angle between two vectors, orthogonal vectors, linear combination. I put these equations over here just as a review. So dot product equation, norm equation, unit vector. So given a vector, you should be able to find the corresponding unit vector. Same thing with the angle between two vectors. One thing I did change, and this is updated in the notes, is whenever you're talking about orthogonal vectors, the main thing that you should think about is the fact that the dot product between them is 0. And that comes from the fact that the cosine of 90 degrees is 0, so therefore u dot v should be equal to 0. So anytime you see orthogonal vectors, you're thinking, okay, they are 90 degrees, they're perpendicular to each other, and the dot product between those two is equal to 0. This will be much easier to deal with and to show compared with this or using that other equation I had, which is updated in the notes, but that's essentially the Pythagorean theorem for vectors. Okay, but this is the one you guys really want to highlight when it comes to orthogonal vectors. Okay, so you should know all of that material. And then we got into solving our systems of equations. So we looked at Gauss elimination and Gauss-Jordan elimination. You should know what REF is and RREF. And how to get to either one. Know your different row operations. So all of that fun stuff. Also, we did use Gauss-Jordan elimination in order to find the inverse. You do not have to do that on your exam. As you know, it is a bear. It takes forever. It's annoying. It's hard to check your work, which means it's also hard to grade. But you do not have to do that on the exam. And so I just wanted to let you know that you don't have to worry about that one. But you should know Gauss elimination and Gauss-Jordan elimination. Once we finished up week B material, then we moved on to determinants, and we learned how to calculate determinants, find all of our cofactors, use those to find determinant, use those to find the inverse. So that's the preferable way, at least for me, to find the inverse. It's much easier to put together, it takes up a lot less space, easier to debug. And then we also did Cramer's rule. So we'll do both of those today. After we did that, we did matrix factorization. We looked at LU factorization and PLU factorization, where LU factorization, we use those same 3 row operations every time. If it's a 3x3, you will not see bigger than a 3x3 on your exam for matrix factorization. And we did PLU factorization, where we did our row swaps. Once again, you will not have to do PLU factorization on the exam. You will only have to do LU factorization. And then next, we did linear independence, all that material that you're applying right now in your homework. We essentially use that to ask the questions of how do I determine the type of system, so if it's consistent or inconsistent, and how do I determine the number of solutions. Sorry, apparently I'm going to be yawning today. Don't know why. Not tired. Got plenty of sleep last night. But determine the number of solutions. 1 solution, infinite number of solutions, or 0 solutions. Those are our 3 options. And the last thing we did was eigenvalues and eigenvectors, which you are still doing in your homework right now. But finding the eigenvalues of a matrix, finding the eigenvectors of a matrix, and writing out the diagonalization. All of that fun stuff is what we've learned in linear algebra. Think about all of the stuff we've learned in this class. Like, you've done a whole bunch of programming, and we've learned all of this linear algebra. Like, there's a lot built into this class, and you should be very proud of everything you've learned and everything you've been able to accomplish. So turn in your homework. Also, if you did not do a homework, go back and do the homework, though. Doing the homeworks is the best way, especially for linear algebra. Doing the homework is one of the best ways you can study for this exam. Okay, so make sure you go do that. Okay, so everything that is in bold, we are going to do today. We are going to take this nice system of equations. It's a fine system of equations. It's not that nice. The numbers are a little big. I did that on purpose. But we are going to solve it using Gauss-Jordan elimination, or Gauss elimination, Gauss-Jordan elimination, finding the inverse using our cofactors, Cramer's rule, and LU factorization. At least that's all I got through this morning. So I'm assuming I'll go through the same stuff for you guys. Okay, so we do not need to find the inverse using Gauss elimination, and we do not need to find the solution using PLU factorization. So let's go ahead and begin. So here's my system of equations. Whenever you have a system of equations, you should be able to write it in the form of AX equals B. AX equals B looks like this. So row 1 comes from equation 1, row 2 comes from equation 2, row 3 comes from equation 3. Column 1 comes from my first unknown, column 2 comes from my second unknown, column 3 comes from my third unknown. And then we have my x vector. Note x1, x2, x3, x1, x2, x3. It's like that on purpose. And then my b vector, -7, -53, and 49. Comes from my constants on my right-hand side. Equation 1, equation 2, equation 3, in that order. And you should know how to do that, and you do. You've been doing it for a while now. Once we have AX equals B, then we can also write our augmented matrix, which is just taking out our x vector. So we know that our solution doesn't really depend on what we call these. We could call them A, B, C, X, Y, Z, X1, X2, X3. It doesn't really matter. So we really only care about our coefficients. So we can write our augmented matrix, which is where we just put our A values next to our B values. There we go. So sometimes, depending on the type of method we are going to use to solve our system, sometimes we want it in AX equals B, sometimes we want it in our augmented matrix. So it really just depends on what you want. Do you want A and B to be separated, or do you want A and B to be together? Okay, so our first method was Gauss elimination. Gauss elimination, the first thing you want to do is you want to write down your augmented matrix. So I'm just going to copy and paste that beauty right there. And then what we want to do is we want to use our row operations to get my lower triangle of zeros. So we've got 3 row operations we can apply. For Gauss elimination, there's no restrictions. You can use any one you want, in any order. Ideally, you want to use them so that they're beneficial. But as you know, probably sometimes you've done a row operation, you're like, oh wait, nope, that didn't help. Okay, so our 3 row operations, we can swap rows. We can rearrange them. Doesn't matter the order in which they are. We can multiply a row by a constant, and we can add a row to another row in order to do our elimination step. So the ultimate goal is to do our elimination steps, but we can use our other row operations to kind of make that elimination step a little bit simpler. Okay, so with Gauss elimination, first, typically what I want to do is I want to put zeros in my first column. So I want a 0 here and a 0 here. So in order to do that, I am going to say that row 2 equals 3 times row 2 plus 7 times row 1. That is the row operation I am applying. I am doing that because I want to use whole numbers. You do not have to use whole numbers. I don't necessarily like to work in fractions. I do better with whole numbers. I don't necessarily like to work with decimals either, because I like my answers to be exact. But you can use any valid row operation you want. So if I multiply row 1 by 7, I get 21, negative 49, 21, and negative 49. If I multiply row 2 by 3, I get negative 21, negative 18, negative 9, and negative 159. So row 1 doesn't change. Row 2 now becomes 0, negative 67, 12, and negative 208. And then for row 3, I'm going to do the same thing, except I'm just going to say row 3 equals row 3 plus row 1. I don't need to change it. I don't need to multiply anything. I just add them together. So it would be 3, negative 7, 3, negative 7, added with negative 3, 5, 7, 49. So I'm going to end up with 0, negative 2, 10, 42. I do want to point out that you should show your work. Michael, you're on the same page as me. For the homework, you can buy more than one row. Yes. But keep in mind, so for the homework, yes, you can combine more than one row operation, one step. So to find my zeros for column 1, if I use row 1 for both of these, I can combine them all into one step. That's pretty simple. That's not a problem. However, make sure that when you are doing your row operations, you're not combining dependent row operations into one step. So if you're replacing row 2 and using row 2 at the same time, so if you're replacing row 2 here, but then you use row 2 in this row operation, those are not independent. So as long as you have independent row operations, feel free to combine them into one step. That's not a problem. One thing to mention in terms of showing your work needs to demonstrate that you know what you're doing, that you know the process. Specifically for your exam is going to be graded heavily on the process. Like you could do a minor math error and still get most of the points. But you need to show that you know what you're doing. So here, when I write this out, I'm not necessarily showing the math operations per se. I'm not saying 21 plus negative 21, but I am showing that I know what I'm doing by multiplying this row by 7 and this row by 2. And then when I do this, like I know because I've taught you, and if you get the right answer, it's clear to indicate that you did add these two rows together. So you need to show your work to show us that you know the process. Because showing us the process will give you most of the points, even if you make a small minor math error. But you can definitely show more than one row operation like I'm showing here if they're independent. That's not a problem. Okay, so I have my zeros in column 1. Now I'm going to move on and put my zeros in column 2. For Gauss elimination, I only care about this one to be a 0. So that means I'm going to say row 3 equals 67 minus 2 row 2. So if I multiply row 2 by 2, I end up with 0, 134, negative 24, 416. If I multiply row 3 by 67, I end up with 0, or if I multiply row 2 by negative 2, sorry. Row 3 by negative 67, or positive 67, I get negative 134, 670, and 2814. So when I add those together, I end up with 0, 0, 646, and 3230. Here we go. I have reached REF, row echelon form. This is one of those terms you should know. You end up with your lower triangle of zeros. So Gauss elimination is reducing the matrix into REF. Once you have REF, you can write your system equations and solve. So this equation, this last equation, essentially if I rewrote it, would say 646x3 equals 3230. If I solve for x3 there, it tells me x3 equals 5. A nice even number. So Nick, that's a good question. You can't, there is no MATLAB function that will get you to REF. Because there are an infinite number of REFs, because there's an infinite number of ways, essentially, that you can apply your row operations. But you can use MATLAB in order to check if your answers are correct. So given a system, you could always type it in to MATLAB. You could say A inverse times B. You could say RREF AB. However you want to type it in, and you can check to see, oh, yep, X3 should be 5. I did that right. This is an upper triangular matrix. Benny, that is a good question. This is an upper triangle matrix with a lower triangle of zeros. So an upper triangle matrix has numbers in the upper triangle. Okay, then with this equation, it tells me that negative 67x2 plus 12, and then x3, I'm going to plug in x3 right away, 5 equals negative 208. X2 here ends up being 4. And then plug those both in here. 3x1 minus 7 times 4 plus 3 times 5 equals negative 7. And x1 ends up being 2. This is an instance where this is sufficient to show your work. You do not need to show all of the algebra steps in order to get to here. You can just show us the process by knowing that, okay, if I write my equations, it looks like this. Here, you're plugging in x2 and x3 right away, and that's fine. You're showing us you know you need to plug in the numbers you already got here. But then you really just need to type this into a calculator in order to get this, and that's fine. But here, you do need to show your work to show your equations. You can't just go from here to here. That doesn't show me that you know what you're doing. That just shows me you can type it into MATLAB. You do need to show this step to write out your equations at minimum to show you know what to do going from REF to get your final solution. And there we go. We solved it. X1 is 2, X2 is 4, and X3 is 5. Woohoo! Method 1 down. Second method was Gauss-Jordan elimination. Gauss-Jordan elimination, very similar. We just want to get more zeros. So if this is REF, and this is my solution, then our REF should end up like this, with identity over on this side, and then my solution ends up over here. So I know that if I'm going to do Gauss-Jordan elimination, and I've already done Gauss elimination, I know I want my result to end up like this. So if we were doing Gauss elimination or Gauss-Jordan elimination from scratch, I would have my augmented matrix. And I would go through more or less the same steps. I would want to first get the columns in, or get zeros in my first column. I would do the same steps I did up here. I would say row 2 equals 3 times row 2 plus 7 times row 1. Same thing for row 3. If you already have RREF, you do not need to start from scratch. I am just illustrating what we would do if we had to start from scratch. So I would get the same answers I got above. There we go. Zeros in my first column. Then I would move on and get zeros in my second column. I want this to be 0 now and this to be 0 now. So for Gauss-Jordan elimination, I want zeros to be in the upper triangle and the lower triangle. So my row operations would look like this. I would say row 1 equals 67 row 1 minus 7 row 2. So if I multiply row 1 by 67, I get 201, negative 469, 201, negative 469. If I multiply row 2 by negative 7, I would end up with 0, positive 469, negative 84, 1456. And then for my this 0 here, I would do the same row operation I did up here. Row 3 equals 67, row 3 minus 2, row 2. So after that set of row operations, I would end up with 201, 0, 117, 987, 0, negative 67, 12, negative 208, and then 0, 0, 6, 46, 32, 30. And then I want to get zeros in my last column. I want this to be 0 and this to be 0. In order to make those easier to accomplish, I'm going to divide this last row by 646. So you would show on paper, but essentially it would be 1 and 5. I'm just going to erase that because I can. But you would make sure you show that work. Which means it's easier to get these zeros here. I can just say row 1 equals row 1 minus 117 row 3. And row 2 equals row 2 minus 12 times row 3. So for my first row operation, it's 201, 0, 117, 987. And then if I multiply row 3 by 117, I get 0, 0, negative 117, and negative 585. Which means row 1 ends up being 201, 0, 117, and 980. Nope. 0. And this one, there we go, 402. When I was doing this on paper for my notes, I made a mistake here. It was a bear to find, I'm not gonna lie. I had incorrectly multiplied something. I can't remember now, but I incorrectly multiplied something. So the best way you guys can check your work is to make sure you are showing a lot of steps. You don't need to show all of your steps, but like here, I'm showing what I'm adding together. So maybe you can go back and you can say, okay, is that number wrong? Did I do that multiplication correctly? Did I miss a sign? But the more work you show, the more the easier it's going to be to check your work. For the second row operation, row 2 ends up being 0, negative 67, 12, and negative 208. And then row 3 times 12 ends up being 0, 0, negative 12, negative 60. So when I add those together, I end up with 1, negative 67, 0, negative 268. I end up with 0, negative 67, 0, etc. And this one ends up being 1, 0, 0, 1, 5. So, Nick, that's a good question. You're not going to be asked to use MATLAB or write a script file in order to confirm your work for the exam. That's just on the homework. So you technically do not need to use MATLAB at all for your exam. You can use it to check your work, to confirm your work. That is completely up to you, but you will not be asked on the exam to write a script file in order to confirm your answers. Good question. Okay, my last step is to divide this one by 2, or 201, and divide this one by negative 67. When I do that, I end up with my RREF. Which is what we expect. If this is what I got for my REF and this is what I got for my solution, then I should expect RREF to look like this. The format of the final is the same as for the midterm. It's going to be on UB Learns. It's going to be links to box folder files that are watermarked and locked. You will have to solve all of there's 6 problems. You'll solve them on paper. Just like you do your homework, you'll scan in those solutions and submit that to the submission link. Okay, so there we go. I've solved it with Gauss elimination and Gauss-Jordan elimination. Our third method was finding the inverse using Gauss elimination. I'm going to skip that one. Like I said, you do not have to do that on the final. It is a bear. I did do that with this system, and it's annoying. But if you did, you would say A next to identity, and then you do your row operations to say identity, and then A inverse shows up on the other side. The annoying thing about finding the inverse is you have 2 extra columns that you have to keep track of. And those, like, you wouldn't have something that ends up like this. You wouldn't have something that divides nicely until you get to the end. And even then, maybe not at the end. It depends on what your numbers are. So it's just annoying. That's what you would do. That's the process. I'm not going to show it because you don't have to do it. And it's time consuming. So that means our fourth method was finding the inverse with our adjoint matrix. That says inverse with adjoint in case you couldn't tell. Which means whenever we have a system, we can write it from AX equals B. Our solution is always X equals A inverse times B. There's just different methods we can use in order to essentially get there. To find A inverse, our equation is going to be 1 over the determinant of A times A adjoint. So given A looks like this, if you don't remember. And now I'm going to find the inverse. I need to find the determinant and the adjoint matrix. I am going to start this process by finding all of my cofactors, because I need my cofactors in order to find the determinant and to find my adjoint matrix. So for cofactor 1, 1, if you are finding the cofactor for a given matrix or for a given element in your matrix, so for 1, 1, you are going to remove the row and column that it's in, and you are going to find the determinant of your remaining values. So -6, 5, -3, and 7. And then you apply your grid. So for the 1, 1 location, it's always a plus. And then you would move on to your next number. My next number here is -7. So cofactor 1, 2. If I remove the row and column it's in, I get my remaining numbers. And my grid is a minus. And then for C1, 3. this number. I remove the row and column it's in. My remaining numbers. Find the determinant of that, and my grid is a plus. And then you just keep going. So for my next row, it's going to be C21. My grid is a minus. If I remove 2, 1, I end up with these numbers. C22, it's a plus. Remove row 2, column 2. I end up with these numbers. C23, a minus sign. I like to write all of my cofactors out immediately together. That way I can see all the patterns. It's up to you though. And here's my cofactors for my last row. Note if you're looking for your grid, it always starts with a plus here and then it alternates going left and down, going right and down. Okay, so then you have a bunch of 2x2s. So once again, showing your work that you know the process. So you don't have to show -6 times 7 minus 5 times -3, but you could show -42 plus 15. Gives us -27. You could show -49 minus 9. Gives us a 58. -35 minus 18 gives us -53. And then you would just keep going. Cofactors are not that challenging. There's just a lot of small pieces to keep track of. For each cofactor, you need to make sure to remove the row and column that you're talking about. So for 2, 1, you remove row 2, column 1. And then you write down your remaining elements. Find the determinant of those, and then change the sign based on your grid. So there's lots of little steps. Each one, though, is not terribly difficult. Once you have all your cofactors, you can use them to find a determinant, or find your determinant, and find your adjoint matrix. So, the determinant of a matrix, determinant of A. You can use cofactor expansion along any row or any column. I'm going to use row 1 because that's my habit. So I'm going to take 3 times the cofactor for that location, which is -27, plus -7 times the cofactor from that location, which is 58, plus 3 times the cofactor from that location, which is -53. Keep in mind that the cofactor already has the sign change. It has the plus, minus, plus, minus, plus, minus, plus, minus, etc. So make sure you're not doing that twice. So make sure you know what you've already done in each individual location. When you do that, you find the determinant of A is -646. Woohoo, we did it. Okay, so I found the determinant. Now I need to find my adjoint matrix. Which my adjoint matrix is just the transpose of my cofactors. So these are my cofactors. This is where they would be if they were in a matrix. So let's just pretend that all of them are in a matrix. Which means if I want to find my adjoint matrix, I just transpose it. So this first set of cofactors becomes my first column in my adjoint matrix. So -27, 58, and -53. This second set of cofactors becomes my second column. So 64, 30, and 6. And then this last set of cofactors becomes my last column, or 39, -12, and -67. There we go. There's my adjoint matrix. Woohoo! So then to put it all together, A inverse equals 1 over negative 646 times my adjoint matrix. Come on. Copy. Paste. I have A inverse. Benny, if you are told to find the determinant of a matrix, you will not be told which method to use. I encourage you to look for any shortcuts that you can find. So if it's a triangle matrix, just multiply all the elements along your diagonal. But you will not be told to do cofactor expansion along a given row or column. It'll just be find the determinant. Sorry, don't know why I'm yawning again. Find the determinant for a given matrix. But once again, use any of those shortcuts that we talked about if you can. So now if I want to find x, I have A inverse times B. So I'm just multiply this by B, which is negative 7, negative 53, and 49. So if I do this, like I said, I like to keep this out because I don't want to be dealing with small fractions. So just keep it out until the end. Do your multiplication. Negative 27 times negative 7 plus 64 times negative 53 plus 39 times 49. This row, this column, dot product between them. Then this row, this column, dot product. This row, this column, dot product. Once again, you need to show us that you know the process. I'm not going to write it down because we got to keep moving. But here's my first answer. Then I would do first my second one, then my third one. When you do that, you end up with our solution, 2, 4, 5. There we go. Woohoo! Method number 3. Technically 4. Method number 5 was using Cramer's rule. Or Cramer's method. Whatever it was. With Cramer's rule, we need to find 4 different determinants. The determinant of A, we already know from up here that it's negative 646. Then we need to find the determinant of A1. Between these two determinants, I can automatically find x1. So determinant A1, if you remember, A1 is just A with the first column replaced by B. So B looked like this. And then my remaining columns remain the same in A. So here's from B, and these two are from A. Once I find the determinant of this, you can use any row, any column you want. I'm going to do cofactor expansion along my first row, or my first column, which means I end up with negative 7 times this, plus negative 53, and then negative determinant, plus 49 times this determinant. So here's my grid, plus, minus, here's my minus, here's my plus. So I get negative 7 times negative 27 plus 53. Gosh, sorry. 53 times negative 64 plus 49 times 39. So the determinant of A1 ends up being negative 1292. So here I have one number, two numbers. I can find x1. x1 is going to be the determinant of A1 over determinant of A, or negative 1292 over negative 646, or 2. The nice thing about Cramer's rule is we can ask you to find only one number. We could ask you find x1 and not even care about x2 or x3. So you should know all these pieces. For determinant of A2, Same idea, except now, same idea as we did to find A1. Yeah, Benny, let me show you an A2. Except I replace column 2 with B. So column 1 of A stays the same. Column 2 is replaced with B. And column 3 stays the same. So if I want to find the determinant of A2 here, I can use cofactor expansion along any column or row I want. I'm going to do cofactor expansion along column 2. So it's going to be -7 times the cofactor, which is going to be, but my cofactor sign in front of 7 is a negative, so I need to make this a negative number. Then plus -53 times its cofactor, which is 3, -3, 3, 7. The thing with Cramer's rule and cofactors and determinants is you really do need to keep track of all of your signs. That grid, it always starts with a plus in the upper left and just alternate signs going across and going down. So whenever you're supposed to change the sign, you have a negative. Whenever you leave it alone, you have a positive. So you just need to keep track of when you're doing that. Are you doing that when you are calculating the cofactor explicitly, as we did up here? Are you doing that in the middle of doing your cofactor expansion? Like, would you put it out here and just change the -7 or the -7 to a +7 right away? So just keep track of when you're changing the sign. And then lastly, so here it's a minus, so I'm going to change it to -47 rather than +47 right away. So when I do that math, I end up with a determinant of A2 of -2584. When I divide that by the determinant of A, I end up with 4. So for Cramer's rule, we're just finding a bunch of determinants. Determinant of A, determinant of A1, A2, A3. I don't have time to do A3, but the determinant of A3 ends up being -3230, which tells me that x3 equals 5, which we know. That's what we expect, because we've already solved it using 3 methods. Okay, the last method we have time for, method number 6, is LU factorization. For LU factorization, what we're going to do is we're going to take A. Let me copy and paste it down. And we're going to apply those row operations. It's the same 3 row operations every time. R1, nope, not that one. R2 equals R2 plus some multiple of row 1. R3 equals row 3 plus some multiple of row 1. And R3 equals row 3 plus some multiple of row 2. You have no freedom in this. These are the 3 row operations you are going to apply. So for my first one, I say row 2 equals row 2 plus 7/3 row 1. And then for my second one, I'm going to say row 3 equals row 3 plus 1 times row 1. So when I do that, I end up with this. I'm not going to show the work. You should show the work, obviously, but I don't have time to write everything down. So when I do that, I end up with 3, -7, 3, 0, -67/3, 4, and 0, -2, 10. My last row operation is row 3 plus negative 6/67, row 2. And I end up with this matrix. I have no choice but to work with fractions. Whatever you end up with ends up being U. That is U. That is your upper triangle matrix with your lower triangle of zeros. L is going to be constructed using these numbers. Keep in mind, though, the sign changes. So L21 is going to be negative 7/3. L231 equals negative 1. And L32 ends up being positive 6/67. So keep in mind that the sign on these is different. So the one with the sign changed goes in my L matrix. So if you are asked to find L31, and I know I probably said this wrong in lecture, but if you're asked to find L31, or you're asked to use the row operation given L31, you should be able to go back and forth between those two. If L32 equals 10, the corresponding row operation is going to be R2, or R3 equals row 3 minus 10 times row 2. You should be able to go back and forth between these. The 10 here, negative 10 here. So the sign changes. Nick, you can definitely use LU factorization to do Gauss-Jordan. You wouldn't it wouldn't result in a bunch of ugly numbers. It would just result in a bunch of potential fractions. But on your exam, you're going to be given relatively small numbers. I chose an example with bigger numbers just to make it harder for illustration purposes. And to let you know that if you can do this, you can do it with smaller numbers. It'll just be easier. But yeah, you can absolutely always do these same 3 row operations for Gauss elimination. That is completely fine. Not a problem. Once we have L and U, then we can solve our system. So essentially we're writing AX equals B in the terms of LUX equals B, and then we break it up into 2. LY equals B and UX equals Y. So LY equals B. Here's my L. Here's Y. And my B vector. B vector looked like this. Negative 7, negative 53, and 49. Once again, this one tells me that y1 equals negative 7. This one tells me that negative 7/3 times negative 7 plus y2 equals negative 53, or that y2 equals negative 208/3. And this one tells me that I have negative 1 times negative 7 plus 6/67 times negative 208/3. Plus y3 equals 49, or that y3 equals 3230/67. Once I have those numbers, I can plug it into ux equals y. U looked like this. My y values look like this. And then I would just solve. So this last equation tells me that 694/67x3 equals 3230/67, or that x3 equals 5. So all those nice fractions melt away. My handwriting is pretty poor right now. This surface, my computer, it's very smooth. I'm not gonna lie. It's a lot easier to write neatly on paper with the friction of a pencil. Then I plug it into this one. Negative 67/3 x2 plus 4 times x3, which is 5, equals negative 208/3. I can solve for x2. Ends up being 4. And then plug it into this one. 3x1 minus 7 times x2, which is 4, plus 3 times x3, which is 5, equals negative 7. When I do that, I end up with x1 equal to 2. Yeah. There we go. 1 minute to spare. So there's our 6 methods. Gauss elimination. Start with your augmented matrix. Convert it to REF. Gauss-Jordan elimination. Start with your augmented matrix. Convert it to RREF. A little more steps. Inverse with Gauss-Jordan. Know the process. Don't worry about having to do it on the exam. Inverse with your adjoint matrix. Start with A. Find all of your cofactors. Use those to find your determinant. Transpose all of those to find your adjoint. Then you can use it to solve your system by multiplying A inverse times B. Kramer's rule. Find a bunch of determinants. Determinant of A, determinant of A1, determinant of A2, determinant of A3. However many unknowns you have. Then divide them all by A. Determinant of A. LU factorization. Break A up into L and U. You can do that using your row operations. You could technically also do that using your known. So you'll have your notes accessible to you. So if you found it easier to know that L looks like this, and U should look like this, and when you multiply them, then you can set it equal to A. If you found that easier, feel free. Just keep in mind, if you're told that L32 should be equal to 1, it's a 1 in here, but your row operation is going to look like this. Either method is fine. Doesn't matter. Once you have L and U, you can break it up and solve your two systems. Ly equals B and Ux equals Y. Okay. That is it. On Wednesday, we are going to go over practice problems, which should be available to you, if not now, in like 10 minutes. Look through those, go through as many as you can, finish up your homework, and I will see you guys one more time on Wednesday before the exam. Don't worry about PLU factorization. You do not need to do it on the exam. Yep. Which, I mean, PLU is essentially just LU. You just have to do row swaps as well. But constructing L makes it a little more complicated, and then, yeah. So don't worry about that. Okay. I will see all y'all on Wednesday.